Okay, I have 2 o'clock, so I think we're going to go ahead and get started. I want to welcome everybody to the OCB Virtual Webinar Series. We are really pleased with a really large turnout. We had about 141 people register as of this morning. For those who don't know me, my name is Heather Benway. I'm the Executive Officer of OCB, the OCB Program and Project Office, and I'd also like to introduce and acknowledge my co-host, May Mahagan, who is the OCB Communications Officer, and OCB's Administrative Associate, Mary Zawoski, as well as the OCB Scientific Steering Committee. And you can learn more about them on our website under the About pull down. The OCB Project Office is based at Woods Hole Oceanographic Institution, and we receive generous support from NSF and NASA. OCB is a network of scientists working across disciplines to better understand the ocean's role in the global carbon cycle and how marine ecosystems function and respond to environmental change. This bi-weekly webinar series will span OCB's overarching science focus areas, which you can see here in the bright green icons. And you can find our current research priorities at the URL listed above there. So you'll see a lot of breadth with these talks. Given the cancellation of our big annual summer workshop this year due to COVID-19, we wanted to find a way to keep you all connected and engaged and continue to share great new science that we're all doing. We solicited ideas and abstracts from the OCB community a couple months ago, and then the OCB SSC and I went through the submissions to put this webinar series together. If it's well attended and well received by all of you, we might continue beyond this summer. So please share this with your friends and colleagues. You can find a full schedule of talks for the whole summer at the URL listed there. You can also just go to the front page of our website and you'll see it right in the big header on our webpage. This is just a sneak peek of what's coming up for the month of July. The remainder of the webinars will have topical themes with 2 speakers per webinar to broaden access. We're going to put all webinars, we'll record the webinars and post them on our YouTube channel. We will share registration links for each webinar at the URL listed here and also via our e-newsletter and on Twitter. So you'll have lots of ways to get the information. If you like what you see, we invite you to engage more with OCB, get involved. Our website's listed here. We put out a bi-weekly e-newsletter, which you can subscribe to from the front page of our website. Just go to the bottom of the website and you can find a very quick link to subscribe. We are on social media, on Twitter. There's our Twitter handle is listed there, and we're using a hashtag of OCB webinar. And we also have a YouTube channel where we'll be posting footage from recordings of these webinars. And you can also find footage from our previous activities in our summer workshops. If you have any questions, you can reach out to us. This email here goes to all 3 of us in the project office. Just a couple of guidelines on Webex just to get started. All of you attendees out there are muted just to reduce distraction and background noise. We politely ask that you save your questions until after the presentation. If you have a question, please use the Q&A function. The questions will be moderated by me, and the Q&A function, I'll show you on the next slide, but there's a ... if you mouse over the bottom of your Webex screen. And within that ... you'll find the Q&A function. If we don't get to all of the questions, we will certainly share them with a speaker so that he can follow up with you after the webinar. If you join the webinar and find that your internet connection is unstable, I've included the phone dial-in information here, so you can always listen in and then watch it later on with the pictures, with the slides later on the YouTube. So here is a little quick visual on how to use the different functions of Webex. In the upper right-hand corner here, you can change the visual layout. You can find these call-in details that were on the last slide over here on the upper left. There's a chat function here that looks like the iMessage icon. I think only the hosts can see the participants. You should already be muted. And then to leave the webinar, you press the red X. And most importantly, for you all as attendees, you can find the Q&A in this ... So today's speaker is Dr. Jeremy Werdell from NASA Goddard Space Flight Center. Jeremy is an oceanographer in the Ocean Ecology Laboratory at NASA Goddard, where he also serves as the project scientist for the upcoming Plankton Aerosol Cloud Ocean Ecosystem, or PACE mission. Jeremy joined NASA Goddard in 1999, where he's made a career ruminating on the on-orbit calibration of ocean color instruments, the development of remote sensing algorithms, and the validation and application of satellite-derived data products. When not traveling with his family and obsessing about his yard, Jeremy also moonlights as a teacher and student mentor. But if he had to do it all again, he would pursue his real dream of becoming a professional chef. The title of his talk today is Socially Distant by Design: How the Evolution of Ocean Color Remote Sensing Contributes to Aquatic Biological and Biogeochemical Studies. Jeremy, I'm going to make you the presenter, and you can take it away.
All right.
Okay.
Heather, May, thanks so much for the chance to do this. This is really fun. I've been looking forward to it. And I hope this finds everybody well.
I'm going to stop sharing my screen here. There you go, Jeremy. You should be getting the presenter baton.
Sounds good. Let's see. I'll just do the whole screen. All right. Can you see that, Heather? Oop, you're muted. You're muted, but you're smiling, so I'll go with that.
Yeah, just put it in presentation mode. Yeah.
There we go. All right. Well, thank you again for the chance to do this. My topic for this wonderful virtual seminar is ocean color remote sensing, with an eye on what the future might hold for all of us. I realize this is a pretty savvy group who knows a lot about ocean color remote sensing, but I'd hate to leave anybody behind. So just indulge me with 2 slides on how this all works. And frankly, ocean color is really just the scientific or mathematical representation of what your eye is already telling you. If you're looking at some object, any object, its color can inform you or give you some instinct as to its composition or quality. In this case, we're interested in how light interacts with the things we're interested in: seawater. And so if you follow that little cartoon, you can see that happy photons from the sun enter the water column, where their intensity and quality is changed. There's only 2 things that can happen to a photon in any medium: it gets absorbed or it gets scattered. In this case, there's a wavelength dependency to both of those processes. And if you're interested in phytoplankton, they absorb and scatter light a particular way. Some of these photons are lucky enough to be redirected back out of the sea surface into the atmosphere and make it into the field of view of a satellite. And that's what we're interested in. In this case, when we refer to ocean color data, this is the measurement of light intensity at different wavelengths. And just something really quickly to put in the back of your heads, for the most part, these instruments are really wide swaths. And the information that this series of measurements contains is limited to how deep sunlight actually penetrates. So just file it away. It'll be important a little bit later. And here, sorry if that was in your field of view. Gulf Coast, Mississippi River Delta is a nice opportunity over a very short gradient to explore variations in the color of the water. So if you're looking from north to south here, you can see that it appears brown near shore all the way into a deep blue as you go offshore. And if you are to look at the intensity of this light, it might represent itself this way. And so these 5 panels represent the intensity of light from blue on the left over to red on the right. And you can see that the shape of this intensity over this spectrum changes, and those changes represent changes to the color. The satellites pretty much measure these wavelengths and this kind of information, and in turn use an inverse process to estimate what's actually in the water body. And none of this is particularly new. Again, this is a savvy group, and I know you're really interested in what's coming down the pipe in the next couple of years. But to get to that, I want to sit and talk very quickly about what the evolution has been like. So if we understand better where we're coming from, we might understand some of the design choices that had to be made as we're going forward. So CZCS, the Coastal Zone Color Scanner, is the first proof of concept satellite mission to study ocean color. It operated from 1978 to 1986. It was only local coverage, and it only looked at 4 visible colors of light with a 1 kilometer footprint. This is what appeared in my textbooks when I was in grad school and captured my imagination. But how has the field evolved over the last 35 years? Well, here is a really shamefully short history of the evolution of ocean color in 2 panels. Let's talk about the left-hand side first. This is a representation of the colors each of these satellite instruments for which NASA has invested has evolved over time, from CZCS to CWIFs to the 2 MODIS and VIIRS instruments that are currently flying. And you can see that, generally speaking, we're not looking at a lot of additional visible information than we were with CZCS. In fact, over time, you can almost see that we're losing some of this. Now, this isn't entirely fair because these are incredible instruments, and there's been thousands of hours invested in their characterization and their study, and they're really fantastic. But if you shift your view over to the right-hand side here, you see that of the things we're interested in, the wavelengths that it's measuring, most of these instruments have been not stagnant, but just a couple of colors, cherry-picked in really important locations over the spectrum to give you the information you want. Other things that are of interest, of course, are the spatial footprint, and then the temporal repeatability or coverage. And again, just looking at this quickly, you can see that we're generally looking at 1 kilometer, maybe a little bit better, and our coverage is 2 to 3 days. So over this immense amount of time, there's been huge investments, but at the same time, there hasn't been much different going on. And so we've totally nailed it. But you may be asking yourself, okay, I've heard of other instruments. How do we do better than this, and where do we go? And so returning back to this table, we need to note that there are limitations on both physics and on space-ready technologies that impede our ability to improve on all of those things all at once. It's a photon-limited system, so there's only certain things that you can do given the technology that's currently available for you. But that said, there are some really interesting things that have emerged over the past 30 years as well. And if we start at the top, you'll notice that there's been a big investment in doing aquatic research at resolutions finer than 1 kilometer. So you have the Landsats and the Sentinel-2s that are 10 to 30 meters. But what's important to realize here in the context of the trade-offs is that you're still only looking at a small number of colors of the rainbow, and your revisit time is actually degraded. This, of course, would argue for constellations of these instruments. And again, they're really spectacular in what they can do, but these trade-offs are important in understanding where we're going to go next. There are also geostationary missions. We'll come back to that term in a second if it's unfamiliar to anybody. But in a nutshell, rather than observing the whole globe on a repeatable cycle, these are instruments that actually travel in an orbit that rotates with the Earth so that they dwell on certain parts of the Earth. And while that has also allowed us to study things in a better time domain, you can't see the entire globe with a single geostationary instrument. And so you're limited into your field of study here. And then you have an instrument like PACE or the other hyperspectral instruments that are coming down the pipe. You see, hey, well, we're still, 1 kilometer footprint and a 2-day global mission, but its trade is it's going to measure light hyperspectrally. So instead of just looking at several colors of the rainbow, it's going to look at a continuous spectrum of all of them. And so what this basically means for you, the end users, is that you have entered a consumer's market here. And it's important to understand that different instruments and different missions offer different capabilities. And so as you start making your choices as scientists about what you're considering using for your own studies, it's important to understand that depending on what your interests are, you may have to intentionally pick the satellite instruments or instruments that you're going to use, because design choices will dictate whether there are the spectral bands to detect different algal groups, if that's what you're interested in. Different instrument designs, whether you're a push broom or a whisk broom, can also introduce varying sources of image artifacts and their associated uncertainties. This may or may not be important to you depending on what uncertainties you can tolerate in your studies. And it's also important to realize, beyond some of the other obvious things that we've already talked about, temporal repeatability and ground sample distances, that performance can vary across instruments depending on what their original purpose was for. And so if you're a multidisciplinary mission where you're studying clouds and land in the very dark ocean, your instrument needs to be designed in a very particular way to allow for a huge dynamic range of input radiances. So we're living in a really excellent time for all of this, but again, it's best to be informed so that you are the most knowledgeable consumers as possible. So in terms of where we're going, I'm broadly grouping into 5 different categories, and I'll provide an example for each. The first is geostationary, a concept we already talked about a few slides ago. The second is a slight divergence. It's active remote sensing from LIDAR. Now, everything we've talked about so far has been passive remote sensing. These are instruments that just observe how sunlight interacts with the ocean, atmosphere, and land. LIDAR is creating its own light. We'll get to that. Then you have CubeSats, which are becoming increasingly popular. And as Heather mentioned, I am the project scientist for one of these missions, known as PACE. So I'm particularly keen on aspects of multi-angle polarimetry and hyperspectral capabilities, because these are what PACE is going to offer. So I guess I waited 5 to 10 slides in to show my homerism for PACE, but there you have it. We will end with some things that this mission is particularly keen on giving to the community. Now, with that homerism aside, because I'm only giving a couple of examples here, I do want to recognize that this is an international community, and other space agencies have done an amazing job of coming up with technologies and sharing. And so I invite folks with interest in learning about capabilities that I'm not discussing here today to become informed with the International Ocean Color Coordinating Group. They're very easy to find, ioccg.org, and I will in particular refer you to the resources tab, where you can learn all about the other missions and instruments that they are tracking. Okay, so moving on to geostationary here. One quick animation to indicate the difference between low Earth orbit instruments, which is generally what we're talking about when we're very casual about discussing ocean color. This is where you get your global repeatability. Basically pole-to-pole coverage of satellites, whether they're ascending or descending. And when I'm talking about global coverages and swaths, this is a representation of what that means. And the width of these swaths change depending on your instrument and its capabilities. When we're shifting to geostationary, again, we're dwelling on a particular part of the globe. And so in this case, you can see that these 2 GOES satellites are rotating with the Earth, and so they are dwelling. And there's a lot of interesting things that can be done if you do this. And we'll get to that on our next slide here. So one example of a geostationary mission coming down the pipe is known as GLIMMER. This is an Earth Venture Award from NASA, scheduled for launch in 2026, 2027, of course, pending when we all get back to work and lay hands on hardware again. But this is exciting because it is also a hyperspectral instrument, and it will have an hourly imaging frequency. And so this is a big innovation relative to a polar orbiter. In this case, you are watching the same spot on Earth all day. Of course, as we mentioned before, what you concede, unless you have a network of these, is that it is targeting the Gulf of Mexico and areas around that. So if you live in another part of the world that you want to study, this particular instrument is not going to be useful for that. But talking about geostationary again and what it offers in terms of its temporal capabilities, there are 3 big science objectives for the science team associated with GLIMMER. all related to what you can learn by studying something from space over time. First, phytoplankton growth and physiology. Unlike a polar LEO orbiter, since you are looking at the same place on Earth over the course of the day, you can do a more informed job of looking at things like growth rate. You can also look at high frequency fluxes of material transitioning from land to oceans. Shorter term coastal processes than you can understand by looking at polar orbiter data. And then, of course, there's a lot of applications that you might imagine are useful for this as well, such as tracking oil spills or the evolution of harmful algal blooms. So there are trades made when you pursue geostationary instrumentation, but there's a lot of new and exciting science that hopefully this community can look forward to with this data stream. Okay, moving on to our second one, LIDAR, which stands for Light Detection and Ranging. So in this case, it's a pulsed laser that measures ranges. And in this case, it's a range and a signal that returns back to the instrument itself. What is really interesting about this is that it gives you some information about vertical structure. So think back to one of my first slides when I asked you to put a pin in it regarding a wide swath instrument that is only able to detect what sunlight can enter the water, as far as sunlight can enter the water and return. In this case, you can look much farther into the water column and you can see layers as well. The disadvantage in the trade, of course, is that this is not a wide swath instrument. This is a narrow track instrument. It's a point of light going by. But there are a lot of interesting things you can do. So I'm going to highlight some work from the Behrenfeld group at Oregon State University that have spent the past half decade or so trying to understand the capabilities of LIDAR for aquatic applications. And there's a nice evolution of papers I'll refer you to if you're interested in such things. The first was just simply an evaluation of, does a LIDAR signal itself tell you anything about plankton stocks? And the good news is that it does. Calliope is a single wavelength instrument. I believe it's 532 nanometers, but that's a useful wavelength for understanding backscattering. From that, there's information on phytoplankton and plankton stocks. I included this map to show that with enough patience and with enough data, despite the fact this is a very narrow track, you can eventually aggregate and accumulate enough information to come up with a global picture. So a second study explored polar regions, and this offers another advantage of LIDAR over traditional ocean color remote sensing in that there are viewing geometries for traditional CWIF's pace-like atmospheric correction, that plus cloud cover, plus bright targets like ice that make it very difficult to study polar regions. Calliope, LIDAR, for example, offers an opportunity to fill in some of those spatial and temporal gaps. And so it provides a nice complement to better understand what's going on in some of these more traditionally poorly sampled parts of our Earth. And then last, a new study out in Nature indicated that this vertical information from a LIDAR can be used to study vertical processes. In this case, it was migration of plankton, but it was a nice demonstration that this information does provide something useful in the sense of vertical structure that cannot be captured from a wide swath passive instruments. And so the take-home message here is that there is unique ocean science that is possible with a LIDAR, noting that all of these studies and other studies like it have used things like Calliope, which were not originally designed for aquatic retrievals. If you're thinking about what might be necessary to do so, or to develop a ocean-specific LIDAR, it would include a more penetrative profiling capability where you could at least get through the first photic layer, say a 1 meter scale or resolution, and also the addition of other wavelengths, like perhaps a ultraviolet wavelength that would allow separation of dissolved organics from phytoplankton retrievals. So there you go, LIDAR coming to you soon. Well, with you soon, sorry. coming to you again soon, hopefully. All right, so let's move on to CubeSats. For this case study, I'm going to highlight SOCON, which is the Sustained Ocean Color Observation from Nanosatellite Project, more conventionally known as SEAHAWK and Hawkeye. This is a proof of concept program designed to evaluate the ability to get credible ocean color imagery at a finer scale resolution that's possible with an instrument like CEOS or PACE, say 100 meters, aboard a very low cost CubeSat. And if you look at the graphic up here in the left-hand side, this is just for a sense of scale. SEAHAWK is this little dot under the red arrow with a person next to it for scale. It's really, really tiny, and it's commercial off-the-shelf parts. So there's a lot of things that we could talk about with regards to lessons learned from this, since it's been launched for a little over a year and a half now. But there are a lot of other flavors of ocean color CubeSats coming down the pike as well. So the important takeaway message for the context of this discussion is that this is feasible. And I'll show you a picture that shows how that is so in a second. But again, because it's a small sat, you're looking at a reduced repeatability in orbit. In this case, it's 18 days. They're not long duration instruments. We're hoping it will survive for 24 months. There isn't a lot of onboard storage capabilities, but the benefit is they're really inexpensive. They're commercial off-the-shelf parts. People who are designing these instruments are sharing the architectures and the frameworks so that this can continue to evolve. And with a fleet of these, you might imagine there's a lot of interesting things that you can do. So here is a SEAHAWK image on the left from March of last year, along with a corresponding image from Modus Aqua. These are in Monterey Bay. And I'd just like to point out that, again, if you're interested in qualitative studies or interested in developing some low-cost technologies that can give you some really interesting information, CubeSats provide a really viable path forward. And so, as Gene Feldman and others like to point out when they're discussing SEAHAWK, that this proof of concept has been realized. All right, multi-angle polarimetry. This may not be something that as ocean color satellite scientists we think about all of the time, but it does provide some really useful dimensions of information that we don't have with our conventional instruments. So one really hands-on way to think about what polarimetry might offer is put on your polarized sunglasses and look at the water, and then start tilting your head back and forth. And you can see that the quality and intensity of the light is changing. And so there are instruments that actually measure that very accurately. A little bit more quantitatively here, you have an image of total intensity of light. This is what our satellites are already measuring. If you looked at the polarized intensity of that same image, you can see that you have a whole new view of what it looks like. And then if you look at the degree of linear polarization, which is the ratio of the two, well, now there's a whole nother series of features that emerge. And all of these features carry information that we don't get from things like CEOS or MODIS or VIIRS. So there's a lot of new information to be culled from all of this. On top of it, most polarimeters, particularly those with an eye on aerosol and cloud properties, measure polarized light at multiple view angles. And so rather than being a fixed angle instrument like MODIS or VIIRS, they're looking at a series of angles fore to aft. Again, to highlight pace, there are going to be two small CubeSat-sized polarimeters on its observatory. It is called, one is called HARP-2, and it is a contribution from the University of Maryland, Baltimore County. And then you have a contribution from the Netherlands called SPEX-1. They complement each other. A HARP-2 is designed most specifically for cloud retrievals. It only looks at 4 colors of the rainbow, but an array of angles, 10 angles for 3 of its wavelengths and 60 angles for its red channel. And it's a wide swath instrument, where SPEX-1 is a narrow swath instrument. It has a hyperspectral capability from the ultraviolet to the near infrared, but it only looks at 5 different angles. And its design choices were made to facilitate improved aerosol retrievals. So I bring this up simply to say that polarimetry is real. There's also European efforts to do this on the MEDOF satellites with an instrument called 3MI, but that the design choices inside of these instruments will also provide a wide variety of different scientific options for aquatic retrievals. How, you might ask? Well, the first is just simply with atmospheric correction. That by better understanding our aerosol field, there's additional information that can be used to remove the atmosphere from an ocean color retrieval. And I'll refer you to a paper by Robert Fruin with input from Kirk Noblespeace and others that do a really nice sensitivity study that demonstrate mathematically that uncertainties in atmospheric correction get lower with the inclusion of multi-angle polarimetry. There are a lot of nice studies that support improved estimation of light penetration, water quality, and particle composition. And what you're looking at over here in the bottom right is a panel on the left that shows how the degree of linear polarization relates to the ratio of beam attenuation to total absorption. What's interesting here is that beam attenuation is not something that we can easily get from a traditional ocean color instrument. The panel on the right shows that there's a relationship between degree of linear polarization and non-alkyl particle concentrations as well. So there's some interesting things that can be done here. For the physical oceanographers out there, vector wind speed is retrievable from polarimetry. And I'll note also on finer spatial scales than is possible with microwave instruments. And then finally, and I realize that this is an in-water detection slide, but it does have relevance for a remote retrieval. You can do a better job with target detection by looking at polarized light fields as well. So there's a lot of interesting things that can be done to retrieve parameters that you are going to be interested for your studies as well. And then finally, moving on to hyperspectral, which I saved for last for 2 reasons. One, I figured it is possibly what this audience is most familiar with, but also because if I was running out of time, it was the easiest to skip through for that. But the advent of PACE and other satellites does make a quantum leap in moving from multi-spectral radiometry to spectroscopy. So many of you are climate scientists and you do understand why it is important to have more information or a better tool in the toolbox to identify phytoplankton community composition or to separate phytoplankton from other water column constituents. And the information provided by hyperspectral radiometry allows you to do this in the optical paradigm. What I want to share here is one example that I use when I'm discussing this with, say, management or end users or early adopters, because it paints a different kind of picture, more of a horror story, which again will be familiar to all of you, but at the same time, it provides some urgency for non-climate scientists who have seen algae in a golf course or seen beach closures because of harmful algal blooms and red tides. And so what I focus on when I'm doing this is usually back to what I studied when I was a grad student, which is phytoplankton community composition in the Arabian Sea, where Noctiluca is pushing diatom communities pretty much out the door here. And I can make the argument here that if you're using an instrument like VIIRS and you're looking at the spectral quality of what a diatom might look like versus Noctiluca, which are represented by the different colors here, there's really only one piece of unique information. Whereas if you're looking at a continuous spectrum, you're almost taking your blinders off and seeing the rich diversity and the spectral nature of this that would allow mathematical separation of these two from remote sensing. But getting to the horror story, again, this goes way beyond climate science, of course. So I realize I'm preaching to the choir here, but again, there are different ways to tell its phytoplankton story, and hyperspectral is just the benchmark in driving it home for a diversity of audiences. So I do need to acknowledge that PACE is not the only instrument with hyperspectral capabilities. This is a list of a number of others with hyperspectral nature of various shapes and sizes. And rather than belabor the horror story or get into any of the nuts and bolts of retrieval algorithms, I will refer you to a brilliant series of papers. These are only 6 of many. Check the references in them. But they all tell a very interesting story about the need to evolve to hyperspectral remote sensing for phytoplankton community composition research. So I assume when you're watching this on YouTube later, you can freeze it and look at these papers on your own time. So getting back to PACE very quickly, I do want to point out that relative to those other instruments, it is the first 1 to 2 day global coverage hyperspectral capability being offered. It is also going to tilt fore and aft 20 degrees, which is increasingly a unique capability for satellite instruments, but that does substantially increase the global coverage that is offered. And perhaps of most scientific interest is that it's also measuring down into the ultraviolet. And that's something that hasn't been routinely done with ocean color either. And so the requirement for the instrument is to measure as far down as 340 nanometers, but there is a strong possibility that we'll be able to at least shine light on detectors that allow measurements at 320 nanometers. So going even beyond hyperspectral, extending this spectral range is really, really critical as well. And hopefully you will find PACE to be useful in your everyday life. Let's say 2023. All right, I'd like to end very quickly by just trying to demystify the use of these data. If you're new to the field, I understand that picking up a new tool and wanting to have it as a routine part of your toolbox can be daunting. So since I'm almost out of time, I will spin quickly through 2 slides and then just show you very quickly in a demonstration how easy this is. At least for the products that NASA maintains responsibility for, there is a singular landing page for all ocean color data, both in its native level 1 and level 2 swath coordinate system and as global maps. And if you just head here and look at the data tab, you will land on a page that looks like this. There's also an incredibly active forum, and this is an old slide, but there are, oh gosh, tens of thousands of exchanges where the community, not just our group, has interacted routinely with novices to experts alike, and it's a wealth of information about how to use these data. Speaking of using these data, we offer a tool called CDAS, and the guts of this is in collaboration with BEAM, which is European Space Agency, EUMETSAT, and Copernicus software tool. So it's a collaborative effort, but it is relatively plug and play. That anything you download from that site can be easily analyzed just by using this tool, which is publicly available. And frankly, once you learn how to use it, you can reproduce NASA processing exactly. So if you'll indulge me for just 1 second, I'm going to exit this this presentation, and quickly go online. So now I am on the Ocean Color website that I just showed you. You'll see that this has grown. So there's a lot of additional instruments that we're responsible for now that are available. I've selected Modus Aqua in this case. And this is just the representation of all data available from last Saturday. And if I go ahead, so all I did to get to here was to click on this little box. If I am interested, say, in Chesapeake Bay, which is near to dear where I live, on that map, it brings me to this screen. And then by clicking on this level 2 ocean color file, it automatically downloads. From there, I fire up CDAS. I locate the file. I open it. And you can see all the information associated with the file is here. It's metadata, some information about flagging, and then all of the raster images. So these are all the data products contained in this file. If I have interest in chlorophyll A, for example, I click on that. And now I am actively engaging with the satellite data file from last Saturday in chlorophyll A space. If I move my cursor around, you can see how easy it is to use to get, if you look on the far right side, chlorophyll A values, latitude and longitude, and all the information that you could possibly want to pull from this with a lot of different statistical tools and so forth. So I don't have time, unfortunately, to give a CDAS lecture here, but I did want to make sure everybody was aware that this is approachable. If I can use it, you can use it. And if you want to learn more about it, there's a lot of online resources as well. This is the help page for CDAS. If you go to their documents, the CDAS walkthrough is particularly comprehensive, but for those who don't want to read, there are also YouTube videos as well. So there are some opportunities here. And then finally, my last slide, just because I hate not talking about citizen science, is there's always ways to contribute, and there's some very, very interesting work going on that contributes to this whole effort, including the remote sensing paradigm. On the left is a paper from a former high school student that related Landsat imagery to what we call the Fowler Sneaker Index. There's a senator in Maryland, a former senator in Maryland, that would have an annual event where he'd put on white sneakers and wade into a certain part of Chesapeake Bay and measure how far up his overalls the water came when he could no longer see his sneakers anymore. So imagine it being kind of a Secchi desk. And that citizen science translated into a wonderful community effort, but also some real quantitative analyses. There are regulatory agencies like the EPA that are using this now to better inform harmful algal bloom appearances so that resources can be best managed. And of course, there are a variety of iPhone and Android apps that allow you to do this from home as well. Again, I know I'm preaching to like-minded people here, but I find this to be particularly exciting. So I am deeply out of time. I am sorry. I think I went over my half-hour limit by just a little bit, but I will end with this moment of Zen, which is what I consider to be second only to the moon landing in what NASA has offered our international community. This is a 20-year record of watching Earth breathe from Cios to Modus to Virs in 2.5 minutes. So I won't belabor this because you can easily find it online. You're welcome to this presentation as well. But if you can, try to imagine what this looks like 10 years in the future once we've taken all of these new technologies and all of these new capabilities and started revealing what we can't possibly even imagine we are currently revealing with our existing capabilities. So I'm running out of breath, I'm running out of steam, and I've run out of time. So I will end with this. And I'd also like to acknowledge some contributors to the presentation, Mike, Jean, and Antonio for their content. I really appreciate that. So with that, thank you very much for your time.
Thank you, Jeremy. That was fantastic. I just want to follow on your comments at the end regarding demystification of the acquisition and applications of these ocean color satellite data, and let people know, all of those out there who are listening, that OCB does provide support primarily geared toward early career scientists to participate in really immersive, fantastic community opportunities and activities like the Cornell Satellite Remote Sensing course. The University of Maine has an ocean color remote sensing course every 2 years. And also the International Ocean Color Coordination Group has a summer lecture series every 2 years. And OCB provides travel and tuition support for scientists to participate in those and acquire the skill sets necessary to add these tools to their toolbox. So I just want to put that out there and just look for announcements in our e-news and our other communication outlets to get your students or postdocs involved, or yourselves if you don't have that capability and you want to acquire it. So with that, I wanted to move on. We have 2 questions here so far.
Okay.
The first one is from Benoit Espinola, and it says, can LIDAR overcome cloud cover?
It depends on how it's being used. But the short answer is no, not entirely. It cannot. It still suffers from interference by clouds, but my understanding, it has an improved ability to see through thin clouds, but of course you have to account for that. I will confess it is a little outside my range of expertise, but the short answer is big cloudy day, nope, not
Okay.
yet.
All right, thank you. The second question is from Raiza Shiel. I hope I didn't butcher your name. I apologize if I did. These Seahawks are like drones. Can they be used in local studies such as estuaries?
Oh, sorry, that's a great question, and I'm sorry if I wasn't clear on that. Let me sneak back to. So there is a NASA Global Hawk, which is an autonomous aircraft. What I was describing here was actually a CubeSat satellite named Seahawk. So the short answer is no, they're not drones. They are satellite technology, so they orbit like other satellites that we discussed in this presentation. But yes, they are specifically designed to, at least in the case of this example, to look at fine spatial footprints on Earth. And so they can be programmed to collect data over your region of interest and inform your study, but no, they are not drones. All that said, and I'm just speaking for myself here, these instruments are so small that I don't see why, say, the Seahawk instrument, which is roughly half the size of a box of tissues, couldn't be configured in such a way to be flown on a drone of sufficient size.
Any other, oh, we have another question from Genevieve Ellsworth. Is there a straightforward way to stitch together global coverage satellite data sets to create a longer continuous time series?
Yes, there are tools within CDAS that allow that. So it depends on what your end product is, what you want it to look like, but there are a number of binning tools that allow you taking individual images and piecing them together in mosaics. And then there are other tools in there that would allow you to do this in more of a batch mode to cobble together a time series as well. So while I highlighted here that this is a graphical user interface for CDAS, everything that you might want to do by navigating the GUI is also possible from the command line as well. So recipes can be put together, say on a Unix platform that allow you to do a lot of batch processing that would support what you're asking about.
Benoit asks a follow-up question. Are there tools to facilitate use of data with multiple platforms, i.e. intercalibration?
I'm not sure so I may not understand the question perfectly, but in the sense of something like CDAS, it is largely agnostic to what data set you ask it to read. So in this case, I showed you a Modus Aqua image, but CDAS and Beam can open several dozen different satellite images ranging from the Sentinels to CZCS. And in fact, it has a generic NetCDF reader. So if, for example, you had some interest in opening a MODIS scene and a VIR scene at the top of the atmosphere to try to do some cross-calibration, then a tool like this would allow that. But it also touches on something else that's interesting that I didn't discuss, is that at least what we produce, the output files are NetCDF. And so, frankly, anybody who has an interest in programming and can read a NetCDF file will have all the information they want to open the satellite data files that at least we produce and do any of that cross comparison or intercalibration activity that you might desire.
Thank you. Is there any satellite that has resolution fine enough to see data from rivers?
I guess it depends on how wide your river is. We didn't talk about commercial satellites here, and it's another interesting topic. Um, so the Landsat Sentinel B series of instruments are between 10 and 30 meters in spatial footprint. And so conceptually, there are a large number of rivers that they would inform upon. I bring up commercial satellites because there are other ones that we didn't discuss that are, for purchase or emerging. Worldview, for example, that have even finer scale spatial resolution, and that would be maybe a different process to acquire, but at the same time, they have the footprint that would open up a new series of rivers that you could study.
Great, thank you. Any other questions?
So I either covered everything or was that bad?
I'm not seeing anything coming across just yet. Bono says, yay, Jeremy. So there's a thumbs up.
She's biased. But I appreciate it.
Just to reiterate, we will be, this has been recorded, so this will be posted on our YouTube channel. We will be sure to put out a shout in our e-news and on our website and on Twitter, just to let people know that it's there. So far, just positive feedback on a great presentation. So
I had a lot of fun putting it together, and this has been a wonderful change of pace, no pun intended, for me. So I hope those in the audience got something out of it. But I appreciate the invite to do this. This is great.
well, thank you very much, everybody, for attending, and we hope to see you on future OCB webinars. Thank you, everybody.